The image came back on July 12, 2022, and the room went quiet. NASA had promised something extraordinary. Decades of engineering, $10 billion, and a mirror the size of a tennis court, folded into a rocket and launched toward a point in space 1,000,000 miles from Earth. Astronomers had been waiting for this moment for over 20 years. They had their predictions ready, their simulations printed, their expectations firmly in place. And then the first image loaded. It showed a patch of sky so small that if you held a grain of sand at arm's length, that grain would cover it completely. Inside that grain of sky, there were thousands of galaxies, spirals, ellipticals, smeared arcs of light bent by gravity, galaxies so far away their light left before complex life existed anywhere we know of. All of it sharp, all of it real, all of it captured in roughly 12 hours of observation. The crowd applauded, but among the scientists, something else was happening underneath the celebration. The colors were wrong, the distances were wrong, the sizes were wrong. Several galaxies in that first image were already triggering quiet alarms in the minds of cosmologists who knew exactly what the numbers meant. Here is what they expected. When you look deep into space, you look back in time. Light travels fast, but the universe is vast. The light-reaching web from the most distant objects left its source billions of years ago. Astronomers expected that the further back they looked, the younger and messier everything would appear. Tiny proto-galaxies, irregular clumps of gas just beginning to collapse, faint, chaotic structures, slowly pulling themselves together under gravity. That was the prediction, built on decades of theory, and confirmed, or so everyone thought, by the older Hubble Space Telescope. Webb's infrared eyes could see further and sharper than Hubble ever could. The plan was to confirm the model, fill in the gaps, and study the first generation of stars and galaxies forming in the infant universe. Instead, the images showed galaxies that looked ancient, structured, massive, fully assembled at distances that placed them impossibly early in cosmic time. One researcher described the experience as looking at a crime scene where the body is 100 years old, but the building it was found in was only constructed last week. The timeline refuses to add up. The James Webb Space Telescope sees an infrared light which is invisible to human eyes. This matters because the universe is expanding, and as it expands, light stretches. The further away a galaxy is, the more its light stretches into infrared wavelengths by the time it reaches us. Webb was designed precisely to catch that stretched light, to peer into an era Hubble could only glimpse at the edge of its vision. What Webb saw in those first hours was the beginning of a crisis in cosmology. Scientists did not panic publicly. Science rarely works that way. Papers began circulating. Teams started double-checking calibrations. Surely there was an error somewhere. A miscalculation. A contaminated dataset. The instruments were brand new after all. Maybe the redshift measurements needed refinement. Maybe the brightness estimates were off. But the checks came back clean. The numbers held. And the galaxies in that first image were exactly where they appeared to be. Something in our model of the universe was wrong. The question was how wrong. And as more images came in over the following months, it became clear that the first deep field was not an anomaly. It was a preview, because sitting inside that data, almost unnoticed at first, were galaxies so old they predated what physics said was possible. And understanding why requires going back to the very beginning of everything. Before Webb broke the model was beautiful. Cosmologists had spent decades building a precise, elegant picture of how the universe went from a hot, featureless explosion to the structured cosmic web we live inside today. It had a name, lambda cold dark matter. And for a long time, it worked almost perfectly. Here is how the story was supposed to go. The Big Bang happened roughly 13.8 billion years ago. For the first few 100 million years, the universe was a sea of hot gas, mostly hydrogen and helium, with no stars and no galaxies. Gravity was the only sculptor, and gravity, given enough time, pulls things together. Spread through that early gas was a mysterious substance called dark matter. You cannot see it, touch it, or detect it directly. But it has gravity, and that gravity created invisible scaffolding across the early universe. Regions where dark matter clumped slightly denser than their surroundings began pulling in regular matter, hydrogen and helium, toward them. Over tens of millions of years, that gas compressed, heated up, and eventually ignited into the first stars. Those first stars lived fast and died violently. Their explosions scattered heavier elements into the surrounding gas. More gas collapsed. More stars formed. Slowly, over hundreds of millions of years, clusters of stars began merging, growing, and organizing into the first primitive galaxies. The key word in that entire sequence is slowly. Galaxy formation, according to the model, is a gradual process. A galaxy the size of our Milky Way takes billions of years to build. It requires multiple generations of stars to live and die, countless mergers between smaller systems, and a steady accumulation of mass over cosmic time. You cannot rush it. The physics does not allow shortcuts. Astronomers knew this. They built it into every simulation they ran, and when they pointed Hubble into deep space and saw increasingly small, irregular, chaotic galaxies at greater distances, it confirmed what the model predicted. The universe looked younger the further back you looked. Exactly as expected. Webb was supposed to sharpen that picture, see the very first galaxies just beginning to flicker on, catch the earliest, messiest stages of galaxy formation in the act. Imagine you are watching a time-lapse of a city being built. You expect to see empty land first, then foundations, then half-finished buildings, then the completed skyline. Webb was designed to show us the empty land and the foundations. Instead, it found skyscrapers. Fully built, fully lit, standing on land that, according to every clock we have, had only just been cleared. The problem is not just philosophical, it is mathematical. The universe has a speed limit for building structure. Dark matter needs time to clump, gas needs time to cool and collapse, stars need time to form, live, and die. You cannot compress those processes beyond a certain point without violating the underlying physics. And yet the galaxies Webb was finding seemed to have done exactly that. Some of them appeared at distances corresponding to only 300 million years after the Big Bang. That sounds like a long time. But on a cosmic scale, 300 million years is an eye blink. Our entire planet formed 4.5 billion years after the Big Bang, and the galaxy it sits inside had been building itself for billions of years before that. The galaxies Webb found at that early timestamp were enormous. Bright, chemically complex, structured. Every one of those properties requires time. Time the universe had not yet had. The model said these galaxies should look like scattered campfires. Webb found blazing cities, and the deeper astronomers looked, the stranger the story became. The paper landed in February 2023, and it sent a quiet shockwave through cosmology. A team of astronomers analyzing Webb's early data had identified 6 galaxies. Each one existed between 500 million and 700 million years after the Big Bang. Each one was enormous. One of them, if the measurements held, contained roughly as many stars as our entire Milky Way galaxy holds today. That alone was alarming. But what made the paper explosive was the phrase the lead researcher chose to describe the finding. He said these galaxies were so massive, so early, that they were, in his words, candidates for breaking the cosmological model entirely. Scientists rarely talk like that. To understand why those 6 galaxies caused such alarm, picture the standard cosmic timeline as a construction project on the world's tightest deadline. You have just received the keys to an empty plot of land. You have 300 million years to build a skyscraper. Every floor requires a specific sequence. Foundation first, structural frame next, floors poured in order, interior work last. You cannot skip steps, you cannot compress the schedule beyond what the materials allow. The galaxies Webb found were finished skyscrapers, standing on land that had barely been cleared. The mass of a galaxy carries a history inside it. Stars take millions of years to form. For a galaxy to contain hundreds of billions of stars, those stars must have formed over an extended period, gone through multiple generations, and accumulated inside a gravitational structure large enough to hold them. Every shortcut you try to take in that process runs into a hard, physical limit. And yet, there they were. The team ran every check they could. They tested whether the galaxies were at a closer distance than the redshift implied, which would make them smaller and less alarming. The data held. They checked whether the brightness was being amplified by gravitational lensing, where foreground mass bends background light and makes it appear brighter than it is. Some amplification was present, but not nearly enough to explain the discrepancy. They checked whether the mass estimates themselves were somehow inflated by unusual star populations. The corrections were minor. After all checks, the galaxies remained enormous and ancient and early. One of the 6 carried a mass roughly 40 billion times greater than our own star. At the time it existed, the universe was roughly 4% of its current age. To put that in human terms, imagine meeting a fully grown adult who claims to be 4 years old. Clothes fitted, vocabulary intact, a career already in progress. The implications split astronomers into 2 camps almost immediately. One camp argued these galaxies proved the standard model, needed significant revisions, possibly a complete overhaul. The model's predictions for how quickly mass could accumulate into structures was clearly off. The question was how far off, and what the fix looked like. The other camp urged caution. Webb was a new instrument. Its calibrations were still being refined. The photometric redshifts being used to estimate distances, measuring color shifts across multiple wavelength bands rather than capturing a full spectral signature, carried uncertainties. It was possible, they argued, that some of these galaxies were closer than they appeared, but the spectroscopic confirmations began arriving. One by one, precise measurements locked in the distances. The galaxies were where the first estimates said they were. The model had a serious problem, and the 6 galaxies from that February paper were only the beginning of the evidence piling up against it. Size is everything. You can forgive a galaxy for being slightly brighter than expected, or slightly further along in its chemical evolution than the models predicted. Astronomy deals in estimates, and estimates carry error bars. But mass is different. Mass is the fundamental currency of cosmology. When the mass of an early galaxy comes back wrong, something deep in the model is broken. Here is why size matters so much in this context. Every galaxy in the universe grew by accumulating mass over time. That mass came from 3 sources: gas collapsing inward under gravity, stars forming from that gas, and smaller galaxies merging together to build larger ones. All 3 processes take time, long stretches of time, and they can only happen after dark matter has already formed the invisible skeleton that anchors the whole structure in place. Dark matter forms its scaffolding first, then regular matter falls in, then gas cools, then stars ignite, then those stars explode and enrich the gas with heavier elements. Then another generation of stars forms from that enriched gas. Each step depends on the previous one completing. You cannot overlap them significantly. The physics enforces the sequence like a locked door. Step 1 must finish before step 2 can begin. Our own Milky Way is a useful measuring stick. It contains somewhere between 200 billion and 400 billion stars. Astronomers estimate it took roughly 10 billion years to build to its current size. That timeline is consistent with the model. It lines up with the dark matter scaffolding, the merger history, the observed chemical gradients inside the galaxy. Everything fits. Now take one of the massive early galaxies Webb identified. Place it at a point in cosmic time when the universe was only 300 to 500 million years old. Give it a stellar mass comparable to the Milky Way, or in some cases, significantly larger. The model says that mass should require billions of years to accumulate. The universe at that point had been around for a fraction of that time. Imagine trying to fill a swimming pool using a garden hose, but someone tells you the pool was already full before you turn the hose on. The pool exists. The water is real. The hose cannot explain it. Some researchers tried to propose that early star formation ran faster than current models allow. Stars forming at rates 10, 20, even 100 times higher than anything we observe in the local universe today. That would compress the timeline. But it creates its own problems. Star formation at those extreme rates produces enormous amounts of radiation and stellar wind, which blows gas out of young galaxies and actually slows further growth. The fix breaks something else. Others suggested dark matter halos in the early universe clumped more efficiently than simulations predicted, giving gravity a head start on building structure. Possible. But the required efficiency pushes against observational constraints from the cosmic microwave background, the oldest light in the universe, which shows us how smooth and uniform matter was just after the Big Bang. The core problem, stripped down to its essentials: galaxies need time to get big. The universe did not have that time. And Webb keeps finding more of them. Each new confirmation adds weight to the same conclusion. Something about the early universe was fundamentally different from what the model assumed. The precise nature of that difference is still being argued, but one word keeps appearing in the papers: impossible. And the next discovery takes the impossibility even further. Astronomers had a name for it: the cosmic dawn. It referred to the era when the first stars switched on, somewhere between 100 million and 500 million years after the Big Bang. Before that moment, the universe was dark. Literally. No stars, no galaxies, just a thin fog of hydrogen gas, slowly cooling in the expanding blackness, and the invisible architecture of dark matter quietly pulling matter toward its densest points. The cosmic dawn was supposed to be the universe's rough draft, messy, tentative, the first fragile sparks of starlight in a universe-wide darkness, scattered and dim, struggling to hold together against the forces trying to tear them apart. Every simulation built to model this era produced similar results: small, irregular blobs of light, loosely organized collections of young stars, barely distinguishable from the surrounding gas. bright in ultraviolet light, because young stars burn hot and blue. But structurally simple, physically small. The first hesitant brushstrokes of a painting that would take billions of years to complete. Webb was pointed straight at that error, and the images that came back looked like someone had replaced the rough draft with a finished manuscript. One of the most striking findings involved not just individual galaxies, but the variety of galaxy types present at that early date. The standard model predicts a narrow range of structures during cosmic dawn. You expect young, irregular, gas-rich systems, possibly some early ellipticals beginning to take shape. The range of possible forms is limited because there simply has not been enough time for different evolutionary paths to diverge very far. Webb found spirals, disks, barred structures, smooth ellipticals already depleted of star-forming gas. All of these forms require either significant time to develop or specific physical processes that were not supposed to be operating at that early stage. One team, examining a sample of early galaxies, found that the structural diversity they observed matched what the standard model predicted for galaxies roughly 3 billion years more evolved. The early universe, according to Webb's images, looked several billion years older than it actually was. There is a useful way to picture this. Imagine receiving a photograph labeled as a newborn nursery. You look at it and see toddlers. Some of them are walking confidently. One appears to be reading. The label says 48 hours old. You check the hospital records. The date is correct. The children are real, and you have no explanation for how they got from newborn to toddler overnight. That is the experience Webb delivered to cosmologists studying the cosmic dawn. The trust signal here is important. The structural observations are confirmed. The distances are confirmed through spectroscopic measurements. The debate is entirely about what these confirmed observations mean for our theoretical models, not about whether the observations themselves are accurate. And the models are struggling. Simulation teams have been running new versions of their programs with adjusted parameters, trying to reproduce what Webb sees. Some come close, none fully match the data. To reproduce the observed diversity and structural maturity of cosmic dawn galaxies, the simulations require conditions that do not match other confirmed observations of the early universe. Something is genuinely, measurably off, and one specific galaxy, confirmed in 2024, pushed the strangeness to a level that forced even the most cautious cosmologist to stop and pay attention. In October 2024, astronomers announced a confirmation that rewrote the record books. A galaxy designated as the most distant spectroscopically confirmed object ever observed had its distance locked in. The light reaching Webb from this galaxy left its source roughly 13.4 billion years ago. The universe at that moment was only 300 million years old, 2% of its current age. The galaxy itself is not enormous by modern standards. Compared to the giants that dominate today's universe, it is relatively compact, but that is almost beside the point. The unsettling thing about this galaxy is its light. Specifically, the kind of light it is producing. When astronomers analyzed the spectrum of this galaxy, they found strong emission lines indicating active, vigorous star formation. Stars were forming inside this galaxy at a rapid rate. That alone is expected for young galaxies. Young galaxies burn fast, but alongside the star formation signal, there were also chemical signatures, evidence of elements heavier than hydrogen and helium already present inside this galaxy. Heavier elements, everything beyond hydrogen and helium on the periodic table, only form inside stars. They are forged in stellar cores over millions of years and released into space when those stars explode. For a galaxy at this distance, at this age, to already contain detectable quantities of heavier elements, it means that at least one full generation of stars had already lived, burned through its fuel, and died before this galaxy even appears in our data. That chain of events takes time, minimum tens of millions of years, possibly longer, and this galaxy already existed at 300 million years after the Big Bang, which means the stellar generation before it, the one that produced those chemical signatures, had to have formed and completed its entire life cycle even earlier. We are looking at evidence of a generation of stars we have never directly observed, whose existence we can only infer from the chemical fingerprint they left behind. The light from this galaxy is unsettling precisely because it is a message written by things that no longer exist, transmitted across a distance so vast that by the time we received it, entire civilizations could have risen and collapsed in the time the signal was traveling. And the message says, we were already here. We had already lived. The story started before the chapter you thought was the first one. The confirmed distance, combined with the chemical signatures, sets a hard lower limit on how early star formation must have begun in at least some regions of the early universe. earlier than any simulation running before Webb's launch predicted. This galaxy is a clue, a piece of evidence pointing at something we have not yet identified. Some process in the very early universe that compressed the timeline of stellar evolution far beyond what the models allow. There is a theory about what that process might involve. It requires imagining a kind of star that no longer exists anywhere in the observable universe. A kind of star so massive, so bright, and so violent that it reshaped everything around it in an extremely short period of time. That story comes next. Before going further, there is one concept worth understanding clearly, because almost every impossible galaxy Webb has found depends on one measurement tool, and understanding that tool is what makes the impossibility real rather than abstract. The tool is redshift. Here is how it works. Light travels as a wave, like a sound wave. Its frequency determines how we perceive it. High-frequency light appears blue to our eyes. Low-frequency light appears red. When a light source moves away from you, the waves stretch out, shifting toward the red end of the spectrum. When it moves toward you, they compress, shifting toward blue. This is the same effect that makes a passing ambulance's siren drop in pitch as it moves away. Now apply that to the universe. Every galaxy beyond our local group is moving away from us because space itself is expanding. The further away a galaxy is, the faster it is receding and the more its light stretches. By the time light from the most distant galaxies reaches Webb's mirror, it has stretched so far beyond visible wavelengths that it only exists in infrared. That is precisely why Webb was built with infrared detectors. The amount of stretching is called the redshift value. A redshift of 1 means the light's wavelength has doubled since it was emitted. A redshift of 10 means it has stretched to 11 times its original wavelength. Astronomers use this value as a distance ruler. By measuring how much a galaxy's light has stretched, they can calculate how far away it is, and therefore, how long ago that light was emitted. When Webb began returning redshift measurements for early galaxies, many came back with values between 8 and 16. Each step up that scale corresponds to an earlier and earlier period in cosmic time. A redshift of 10 puts a galaxy at roughly 450 million years after the Big Bang. A redshift of 14 pushes it back to around 300 million years. The confirmed galaxy from the previous chapter carries a redshift value above 14. Now here is where the impossibility becomes precise. The early measurements of many Webb targets came back as photometric redshifts. These use multiple images of the same galaxy taken at different wavelengths to estimate the redshift, essentially triangulating the answer from the shape of the light curve. They are fast and useful, but they carry error ranges. The spectroscopic conformations are the gold standard. They spread the galaxy's light into a full spectrum and identify specific chemical fingerprints. Those fingerprints only appear at exact wavelengths in the lab. How far they have shifted from those exact wavelengths gives a precise confirmed redshift value. When spectroscopic confirmations started coming in for Webb's early galaxy candidates, the expectation inside the community was that some of the most extreme photometric estimates would soften. The error bars would shrink toward more reasonable distances. The most alarming cases would turn out to be closer than initially measured. The opposite happened. Several targets came back with confirmed redshifts, at or exceeding the photometric estimates. The galaxies were as far away as feared, or further, and at those distances, with those confirmed ages, their masses and brightness levels remained as alarming as the first measurements suggested. The ruler works. The distances are real. The numbers are not coming back wrong because of measurement error. They are coming back impossible because the universe in its early chapters behaved in ways our model did not predict. And the next layer of strangeness does not involve distance at all. It involves what is inside these galaxies. Specifically, the age of the stars already living in them when Webb caught their light. This is the detail that stopped many researchers cold. When Webb analyzed the light from some of the earliest confirmed galaxies, the spectral signatures revealed something unexpected inside them. Alongside young, hot blue stars, there were old stars. Red, cool, evolved. Stars that had already burned through the fast, bright phase of their lives and settled into their long, slow decline. Old stars require time to become old. That sounds obvious, but the implication is severe. A young star burns hot and emits mostly blue and ultraviolet light. As it ages over millions to billions of years, depending on its mass, it swells, cools, and shifts toward red wavelengths. The presence of these red evolved stellar populations inside a very early galaxy means those stars had already gone through a significant portion of their lives before Webb captured the galaxy's light. Think of it this way. You are looking at a photograph of a crowd taken at a high school. Some of the people in the photograph are clearly elderly. Grey hair, lined faces. If the school only opened last year, something is deeply wrong with your understanding of when these people were born. That is the logical structure of what Webb found. Galaxies that were themselves young, measured by their distance and confirmed age in the universe, but already containing stellar populations old enough that they should not have had time to age that far. In several cases, astronomers estimated that the red stellar populations inside these early galaxies were already hundreds of millions of years old at the time the observed light was emitted. Some estimates pushed further. Possibly as much as 1 billion years of stellar evolution had occurred inside galaxies that existed in a universe younger than 1 billion years. The overlap is nearly impossible. This finding directly affects something called stellar archaeology, the practice of reading a galaxy's history from its current stellar population. Astronomers use the mix of stellar ages inside a galaxy as a record of its past. A diverse mix with both very old and very young stars tells a long history. A galaxy dominated by young stars tells a short one. Early galaxies by the standard model should tell very short histories. They have not had time to accumulate multiple generations of stars. Webb found several telling histories that required more time than the universe had provided. The confirmed presence of evolved stellar populations at these redshifts is one of the most difficult observational results for current models to explain. The models require either a radically accelerated rate of early star formation, with stars forming and aging in compressed timescales, or an earlier origin for structure formation than the model currently places. Neither solution is simple. Both require revising fundamental assumptions, and this was not even the most unsettling version of the old stars problem. Some early galaxies did not just contain old stars, they had stopped forming new ones entirely. Galaxies that had gone completely quiet, no star formation, no gas, no activity, just a population of aging stars cooling slowly in the dark. Those galaxies have their own name, and their own deeper mystery. They have a nickname in the field, red and dead. It sounds almost poetic, but the reality is cosmologically disturbing. A red and dead galaxy is one that has exhausted its supply of star-forming gas and gone quiet. No new stars forming, no ultraviolet glow from hot young stellar populations. Just a sea of old, cool, red stars slowly fading over billions of years. In the local universe, the galaxies we live near today, red and dead systems are common. They are usually massive elliptical galaxies that used up their gas long ago and settled into a calm, aging existence. The problem is when they appear. In the local universe, a galaxy becoming red and dead makes sense. It has had 10 billion or more years to form stars, exhaust its gas supply, and go quiet. The timeline is entirely reasonable. You built the whole house, you moved in, you used up all the building materials. Now you just live there. Webb found red and dead galaxies at distances corresponding to just 700 million to 1 billion years after the Big Bang. A galaxy that has gone red and dead has to have first formed, then vigorously formed stars at a high rate, for an extended period, then somehow lost or expelled all of its remaining star-forming gas, and then gone quiet. That entire sequence from first star formation to complete cessation takes time. Based on what we observe in the local universe, that process typically spans several billion years. At 700 million years after the Big Bang, the universe had not yet been around for several billion years. One confirmed example, reported by a team using Webb spectroscopic data, showed a galaxy that had already completed its entire active star-forming lifetime and gone quiet. The analysis suggested this galaxy had formed the bulk of its stars in a burst lasting only 30 to 90 million years, an extraordinary rate. Then it stopped, completely. And it was already dead at a cosmic age when, according to the standard model, galaxies should still be in their most active growth phases, 30 to 90 million years to form an entire galaxy's worth of stars, and then go permanently dark. For comparison, our star took roughly 50 million years to form alone. This galaxy formed hundreds of billions of stars in roughly the same time frame. The intensity required is almost incomprehensible. There is a mechanism that can drive a galaxy quiet: feedback from a supermassive black hole at its center. When a black hole grows large enough and feeds actively enough, it blasts energy and radiation into the surrounding galaxy, with such force that it heats and disperses the star-forming gas, shutting down stellar nurseries across the entire system. This process, called quenching, is observed in the local universe and is a standard part of galaxy evolution models. But those models place quenching late in galaxy evolution, after a long period of black hole growth. At 700 million years after the Big Bang, The black holes themselves should still be small, too small to quench an entire galaxy, unless the black holes were already enormous. And that is exactly what Webb found next. The backbone of every galaxy is invisible. You cannot photograph dark matter. You cannot weigh it directly. Every detector ever built to catch a dark matter particle has come up empty. And yet cosmologists are deeply confident it exists, because without it, nothing in the universe makes structural sense. Galaxies spin in ways that require far more mass than their visible stars can provide. Galaxy clusters bend light in ways that demand invisible mass. The entire large-scale structure of the cosmic web, the vast network of filaments and voids that organizes the universe, matches simulations only when dark matter is included. Under the Standard Model, dark matter is the first actor in the galaxy formation story. In the hot, early universe, dark matter began clumping into what cosmologists call halos, invisible knots of gravitational influence. These halos formed the anchor points around which regular matter could collect. Gas fell into the halos, cooled, and eventually collapsed into stars. First the dark matter structure, then the stars. The halo forms first. Everything else follows. Here is the critical constraint that makes Webb's discoveries so troubling. The size of a dark matter halo limits how much regular matter can collect inside it. You cannot build a massive galaxy inside a small halo. The gravitational depth of the halo determines the ceiling. And in the early universe, halos were small because they had not yet had time to grow through their own mergers and accretion. The Standard Model's predictions for halo mass at early cosmic times set a firm upper limit on how massive galaxies could be at any given period. It is a physical ceiling enforced by gravity, expansion, and time working together. The model does not predict this limit as a rough estimate. It calculates it precisely. Webb's massive early galaxies exceed that ceiling. Some teams have estimated that producing the observed galaxies within standard lambda cold dark matter would require the conversion of nearly 100% of available gas into stars. Every single atom of gas inside those dark matter halos would need to have formed a star. No waste, no outflows, no gas lost to radiation or feedback. Perfect efficiency. Observed star formation in the local universe operates at efficiencies of a few percent, sometimes reaching 10% under extreme conditions. Perfect efficiency has never been observed anywhere. It may be physically impossible. So either the efficiency assumption is wrong by an enormous margin, or the halos themselves were larger than the model predicts at that epoch, or matter assembled into structure faster than the standard timeline allows. One emerging idea suggests that in the very early universe, the behavior of dark matter itself might have been different. The Standard Model treats dark matter as cold, meaning it moves slowly and clumps easily. Some researchers argue that under certain early universe conditions, dark matter could have organized into denser structures faster than current models account for, effectively giving galaxy formation a significant head start. This idea is a theory, not yet confirmed by independent observation, but it addresses the waiting period that the data seems to have erased. Under the Standard Model, galaxies wait for their dark matter halos to mature before they can grow. Webb's galaxies appear to have skipped that wait entirely, as if the scaffolding appeared fully built and the construction began simultaneously, defying the sequence the model demands. The structure beneath the structure failed to slow things down, and that failure points directly towards something that was supposed to grow gradually, something that had no right to be enormous this early: the black holes. Every large galaxy contains a supermassive black hole at its center. That fact is confirmed across thousands of observations. Our own galaxy has one, sitting roughly 26,000 light-years from where you are right now. It contains the mass of roughly 4 million stars compressed into a single point. And by galactic standards, it is considered modest. The supermassive black holes at the centers of some galaxies reach masses of billions of stellar masses. The most extreme confirmed examples push toward tens of billions. These are the gravitational engines that sometimes power the brightest objects in the universe, blazing cores called quasars, where infalling matter heats to extreme temperatures and blazes across billions of light-years. Under the Standard Model, supermassive black holes grow gradually. They start as smaller black holes, potentially remnants of the first generation of massive stars, and accumulate mass over time by swallowing gas, dust, and other matter. The growth is bounded by something called the Eddington limit, a natural ceiling on how fast a black hole can feed before the radiation it produces pushes infalling matter back out. At the Eddington limit, a black hole can roughly double its mass over roughly 45 million years. That sounds fast, but to grow from a stellar mass black hole of perhaps a few hundred solar masses to a supermassive black hole of a billion solar masses, requires roughly 1 billion years of sustained feeding at the Eddington limit. That is the minimum timeline, with no interruptions and maximum possible efficiency. Webb found a quasar, an actively feeding supermassive black hole, at a distance placing it just over 600 million years after the Big Bang. The black hole powering it had already accumulated a mass of roughly 1.6 billion solar masses. 600 million years into a process that takes a minimum of 1 billion years. One analysis put the problem bluntly. If this black hole formed from a stellar mass seed and fed continuously at the Eddington limit from the first possible moment after the Big Bang, the math still does not reach the observed mass in the available time. There are proposed solutions. One involves what cosmologists call heavy seeds, the idea that in the very early universe, some regions of dense gas collapse directly into black holes with masses of tens of thousands to hundreds of thousands of solar masses, skipping the stellar phase entirely. This direct collapse scenario bypasses the slow growth problem by starting with a dramatically larger seed. Direct collapse is a theory, a compelling one, supported by some indirect evidence. But astronomers have not yet directly observed a direct collapse black hole in formation. Webb is searching for them. Another proposal involves periods of super Eddington accretion, where a black hole feeds beyond the theoretical limit during brief intense episodes. Some observations in the local universe hint this may occur, but sustained super Eddington growth over cosmic timescales remains unconfirmed. The confirmed fact is this: Webb has found supermassive black holes that are too massive for the time they occupy. Multiple examples, at multiple distances, all confirmed spectroscopically. And those black holes may be responsible for something even more baffling about the early universe's brightest galaxies. Light tells stories. The brightness of a galaxy tells you how many stars it has, how actively it is forming new ones, and roughly what kind of stellar population it contains. Astronomers have calibrated these relationships carefully over decades, measuring thousands of galaxies across cosmic time. The relationship between mass and brightness, called the mass-to-light ratio, is one of the most reliable tools in observational cosmology. Webb broke it. When astronomers measured the brightness of early galaxies and compared it to their estimated masses, the numbers came back wrong. The galaxies were too bright, significantly systematically too bright across a large sample. Some were producing between 5 and 10 times more ultraviolet light than their estimated stellar masses should allow. A galaxy generating 10 times more light than its mass predicts is not a calibration issue. It is a statement about physics. Either the mass estimates are severely wrong, or the stars inside these galaxies are producing light far more efficiently than stars do anywhere in the local universe. The first option, wrong mass estimates, was investigated carefully. Mass estimates for distant galaxies rely on modeling the spectral energy distribution, the total light output across all wavelengths, and comparing it to stellar population models. These models have uncertainties, but those uncertainties are well characterized. The excess brightness in Webb's early galaxies exceeded the uncertainty ranges by significant margins. The second option leads somewhere genuinely interesting. Stars produce light through nuclear fusion. The efficiency of that process depends heavily on the mass and chemical composition of the star. Massive stars burn hotter and brighter relative to their mass than smaller stars do. And the chemical composition matters because heavier elements, anything beyond hydrogen and helium, affect how energy moves through a star's interior, and ultimately how much light escapes. The very first stars in the universe, formed from pure hydrogen and helium before any heavier elements existed, would have been fundamentally different from any star alive today. More massive, on average. Hotter. Far more luminous per unit of mass. They are called population 3 stars, and astronomers have been searching for direct evidence of them since the concept was first proposed. Webb has not yet directly observed a population 3 star, but the excess brightness of early galaxies is one of the strongest indirect signals that these extreme early stars may have dominated the first generations of stellar populations. Galaxies packed with population 3 stars would blaze with light far beyond what their mass would predict under current stellar models. This is still a leading theory, confirmed by multiple independent teams as a plausible explanation for the luminosity excess. Direct confirmation awaits deeper observations. But the brightness problem does more than hint at unusual stars. It exposes a crack in the standard model, wide enough to drive a significant theoretical revision through. And that revision, when it comes, will have to confront not just the brightness numbers, but the specific type of light these galaxies are pouring into space. Because the most dramatic signal is not visible light, it is ultraviolet. And the ultraviolet output of early galaxies is the single most disruptive measurement Webb has delivered. Picture the universe at 100 million years old. No stars yet, no galaxies, just hydrogen and helium gas, cooling slowly in the dark, falling toward the densest knots of dark matter gravity, had spent millions of years building. The first gravitational traps are set. The gas is beginning to compress. Now picture that gas igniting. The first stars in the universe formed from material unlike anything that exists today. Pure hydrogen and helium, with no heavier elements mixed in. No carbon, no oxygen, no iron, nothing that modern stars contain in small but significant quantities. This chemical purity had a profound physical effect on how those stars formed. In modern star formation, heavier elements act as cooling agents. When gas clouds collapse under gravity, they heat up. Heavy elements radiate that heat away, efficiently, allowing the cloud to cool and fragment into smaller pieces, which each collapse into individual stars of modest mass. The heavy elements put a natural brake on how big any single star can grow. Without those heavy elements, the early gas clouds could not cool efficiently. They fragmented less. The pieces that collapsed were larger, far larger. The result, according to theoretical models, was stars of extraordinary mass, potentially hundreds of times the mass of our own star. Some models predict these population 3 stars could have reached thousands of solar masses, though this remains actively debated. At those masses, they would have burned at temperatures and luminosities that dwarf anything observable in the modern universe. A single population 3 star could have outshone entire young galaxies, and they would have lived fast. The most massive stars burn through their fuel quickly. A star with 100 times average mass might exhaust itself in a few million years, compared to the billions of years a modest star like ours spends on the main sequence. Population 3 stars would have blazed, exploded as the most powerful supernovae ever seen, and seeded the universe with the first heavy elements, all within an eye blink of cosmic time. Their deaths would have been as important as their lives. Those supernovae scattered carbon, oxygen, nitrogen, and heavier elements into the surrounding gas for the first time. The next generation of stars formed from that enriched gas, and the generation after that, each explosion adding more complexity to the chemical inventory of the universe. This is why the chemical signatures Webb finds in early galaxies matter so much. Every detection of heavy elements at extreme distances is evidence of population 3 stars doing their work. We read their biography in the debris they left behind. Webb has not yet captured a confirmed image of a population 3 star. They are almost certainly extinct. The universe ran out of chemically pristine gas long ago, and no region is known to contain the conditions needed to form them today. What Webb is hunting for are galaxies so early, so close to the first light, that their spectra show the characteristic emission signatures of population 3, stellar populations. Several candidate signals have appeared in Webb's data. A few are intriguing enough that dedicated follow-up observations are underway. Confirmation would be among the most significant discoveries in the history of astronomy, and the importance extends well beyond astronomy. Population 3 stars are the origin story of every atom of carbon, oxygen, and iron in your body. The elements that make complex chemistry and life possible did not exist until those first enormous stars died. The universe needed them to fail spectacularly before anything like us was ever possible. That debt runs in both directions, and the evidence for how it was paid is reshaping a theoretical framework that had stood unchallenged for decades. For roughly 30 years, one theoretical framework has dominated cosmology: the lambda, cold, dark matter model. Cosmologists call it lambda CDM. It describes how the universe evolved from the Big Bang to today, incorporating dark matter, dark energy, the expansion of space, and the formation of large-scale structure. It makes precise predictions, and across an enormous range of observations, it has held up with remarkable accuracy. The cosmic microwave background, the oldest light in the universe, matches lambda CDM predictions to extraordinary precision. The distribution of galaxies across vast cosmic distances matches the model's predictions for how matter clustered under gravity over billions of years. The abundance of light elements in the universe matches the model's predictions for what the Big Bang should have produced. Across these and many other tests, lambda CDM performed like a well-calibrated instrument. Then Webb started returning data from the early universe. The tension between Webb's observations and lambda CDM predictions is real, confirmed, and currently unresolved. The question is whether it represents a need for small adjustments within the existing framework, or a signal that the framework itself requires fundamental revision. The adjustments camp argues that some parameters within lambda CDM can be tuned to accommodate early galaxy formation. Perhaps star formation efficiency was genuinely higher in the early universe. Perhaps some feedback mechanisms operated differently under early universe conditions. The model allows some flexibility, and these adjustments might be enough to close the gap. The revision camp argues the gap is too wide. The sheer number of confirmed massive early galaxies, the presence of evolved stellar populations at extreme distances, the brightness excess, the oversized black holes, and the red and dead systems all point in the same direction. The early universe formed structure faster, more efficiently, and more completely than lambda CDM predicted. And the deviation is not marginal. One useful analogy is a clinical trial where the results come back consistently outside the predicted range. A single outlier gets noted. 5 outliers trigger a review. 10 consistent outliers in the same direction force a re-examination of the original hypothesis. Webb has returned dozens of outliers, and they are nearly all in the same direction. The early universe was more mature than the model allowed. The confirmed fact is that lambda CDM, in its current form, does not reproduce Webb's early galaxy observations without modifications. That is agreed upon by essentially all researchers in the field. The debate is entirely about the magnitude and nature of those modifications. And sitting beneath that debate is a deeper question, a question that cuts to the heart of what we think we know about the origin of everything. The question is whether lambda CDM is failing because it needs parameter adjustments, or because one of its core components, dark energy, dark matter, or the assumption that physical constants were the same in the early universe as they are today, was wrong to begin with. Some cosmologists have begun looking at that last possibility very seriously, and what they are finding, piece by piece, may reframe every answer Webb has provided. Science rarely breaks loudly. The textbooks do not get rewritten overnight. The model does not collapse in a single press conference. What actually happens is a quieter process. A small group of researchers begins circulating a paper that makes an uncomfortable argument. Other researchers read it with skepticism. They try to find the error. They cannot quite find it. A few more papers appear, reaching the same conclusion from different angles. The argument begins gathering weight. That is the process currently underway in cosmology. The argument is specific. Galaxy formation in the early universe ran significantly faster than the standard model allows. The evidence for this conclusion comes from multiple, independent measurement techniques, applies to a statistically significant sample of objects, and survives the calibration checks that were supposed to explain it away. The uncomfortable implication is that something about the early universe's physical environment differed from what lambda CDM assumes. Several specific proposals have emerged. One involves the behavior of dark matter at early times. Standard lambda CDM treats dark matter as cold and collision-free, meaning it does not interact with itself, or with regular matter, except through gravity. But some models of dark matter allow for weak self-interactions. Even a small level of dark matter self-interaction could cause it to clump more efficiently in the early universe, building larger halos faster, and giving galaxy formation a significant head start. This idea, called self-interacting dark matter, has been around for decades, but Webb's observations have pushed it back to the center of discussion, because the head start it provides is exactly the kind needed to reconcile the early galaxy masses with an otherwise intact cosmological timeline. Another proposal revisits the concept of primordial black holes. Under certain early universe conditions, density fluctuations in the hot plasma of the infant universe could have been large enough to collapse directly into black holes before any stars formed. These primordial black holes, if they existed with the right mass distribution, could have seeded the formation of early galaxies more efficiently than dark matter halos alone, providing both the gravitational anchor and the central black hole seed simultaneously. Primordial black holes are a theory with ongoing observational tests. Webb itself is part of those tests, searching for specific signatures that would confirm or rule out the primordial black hole scenario for galaxy seeding. A third group of researchers has taken a more radical position. They argue that the star formation rate in the early universe was simply higher than any local observation would suggest, driven by conditions that no longer exist. Dense, metal-poor gas under extreme gravitational compression, in halos more concentrated than lambda CDM predicts, could have formed stars with an efficiency approaching values the model treats as physically unreachable. Each of these proposals touches a different piece of the standard model. Each is a targeted adjustment rather than a wholesale replacement. But they all share a common feature. They require the early universe to have operated under conditions meaningfully different from those the standard model assumes. And one of the most striking pieces of evidence for that difference is not in the galaxies themselves, it is in what sits between them. A discovery so geometrically wrong, so spatially impossible at its confirmed distance, that it forced an entirely separate line of theoretical emergency. Galaxy clusters are the largest gravitational structures in the universe, collections of hundreds or even thousands of galaxies, bound together by gravity and embedded in vast clouds of superheated gas, sitting inside enormous dark matter halos that can span tens of millions of light years. They are the endpoints of cosmic structure formation, the biggest things gravity has ever built, and they take a very long time to build. Under lambda CDM, the timeline for cluster formation is well established. Small dark matter halos form first. They merge into larger halos. Those larger halos merge again. Over billions of years, this hierarchical process builds progressively larger structures, culminating eventually in the massive clusters observed in the local and intermediate distance universe. The process is slow by design. Gravity is patient. Mergers take time. The earliest galaxy clusters in the Standard Model should appear at roughly 2 to 3 billion years after the Big Bang. Before that, the structures needed to anchor a full cluster simply have not had time to go through the required sequence of mergers. Webb found a confirmed protocluster, a bound, collapsing structure containing multiple massive galaxies, on track to become a full cluster, at a distance placing it at roughly 800 million years after the Big Bang. 800 million years, more than a billion years before the model's earliest predicted cluster formation time. The structure contains several spectroscopically confirmed galaxies within a small region of space, moving with velocities consistent with gravitational binding. The galaxies themselves were already massive. The gas surrounding them showed the early signs of the superheated intracluster medium that defines mature clusters in the local universe. Everything about the structure read as a cluster at an age when clusters should not have existed. The dark matter halo required to produce this structure at this distance, according to calculations run by multiple independent teams, would have needed to reach a mass roughly equivalent to a quadrillion times the mass of our own star, all within 800 million years. Under standard lambda CDM, halos of that mass are simply not predicted to exist that early. The mergers needed to build them had not had time to complete. One team described the situation as finding a fully formed mountain range on a planet that had only just cooled from molten rock. The timescale for the geology does not fit the age of the terrain. The cluster finding amplifies every concern raised by individual early galaxies. Galaxy formation being anomalously fast could in theory be explained by local conditions. Unusual gas concentrations, rare but possible density peaks in the early universe. But a full protocluster requires coordinated large-scale structure formation across a volume of space hundreds of millions of light years across. Local explanations do not reach that scale. The finding requires the large-scale matter distribution of the early universe to have been more concentrated, more organized, and more advanced than lambda CDM's initial conditions predict. That goes beyond galaxy formation physics and touches the very starting conditions of the universe.